Hello and welcome back to High Peak Education. I would like to perform a rotational motion problem which uses rotational dynamics, namely force and torque, as well as rotational kinematics, and then I would like to use the conservation of energy as well. Okay, so let's go ahead and take a look at this problem. It says a person applies a force which is tangent to a 0.320 meter disc to spin it. A. How much work is done if a 200 Newton force is applied through a rotation of 1.00 radian, that is 57.3 degrees or so. The force is kept tangent to the disc while it is applied. B. What is the final angular velocity of the disk if it has a mass of 85.0 kilograms? So let's go ahead and start to solve this problem. It looks like we know what the radius of this disk is. That's 0.320 meters. We also know we want to find the work done if we have a 200 Newton force. So the force is 200 newtons. And it's applied the rotation angle, that's delta theta, of 1.00 radians. And we also know that the force is kept tangent to the disk. So the thing is, that's the torque is going to equal to R times F, because R here is just the radius of the lever arm. And so it's going to be exactly perpendicular. We don't need to worry about sine of phi here or anything. So there we go. And let's see. So we're trying to figure out what this work is. Well, in part A, we recall the work, basically force times a displacement. But we note that a displacement now for rotation is an angular displacement. So we should be able to say that the rotational work is equal to the rotational force, which we call torque, times the rotational displacement, which we call delta theta. So the torque we said was radius times force, and the delta theta we also know. So I believe we can just put all those values into this problem. The radius was 0.320 meters. The force was 200 newtons. And then the delta theta is 1.00 radians. So let's calculate this. So for this calculation, we'll take 0.32, the calculator doesn't care about significant digits, times 200. And that should be 64. And again, we want 3 significant digits, so let's do 64.0. So the rotational work is equal to 64.0, and that's not newtons, but joules, because this is rotational energy. Notice that meters times newtons is Newton meters for torque, but radians are unitless, and given that it's energy, we convolve the newtons and meters together to have the units of joules. So that solves part A. Now let's take a look at part B. What is the final angular velocity of the disk if it has a mass of 85.0 kilograms? Well, the mass of 85.0 kilograms and the fact that we know it's a disk, we know immediately the formula for its rotational inertia. That's 1/2 mr squared. Now we remind ourselves, hey, wait a second. Why would we want to know the rotational inertia? Well, it turns out if you know the rotational work, recall the work kinetic energy theorem. The work kinetic energy theorem is that the net work done is equal to the change in the kinetic energy. Recall this theorem. But notice in this case, it's rotational work and rotational kinetic energy. So change in rotational kinetic energy should be like 1/2 I omega final squared minus 1/2 I omega initial squared, because this is the initial rotational kinetic energy and the final rotational kinetic energy. And this I is the same thing as the I of the disk. It's the moment of inertia. Now, by the way, this final rotational kinetic energy should equal 0 joules because the angular velocity we know to be 0, and so we can just set that equal to 0 joules. So notice, if we want to solve for the final angular velocity, let's just take this term, 1/2 I omega final squared equals to rotational work, which we already have, and solve for omega final. So if we multiply both sides of this equation by 2, we have 2 times the rotational work is equal to the rotational inertia times the angular velocity squared. Well, we need to divide by rotational inertia. That's 2 times the rotational work divided by the rotational inertia, and the square root of this value should give the final angular velocity. So let us put the values in to this expression. So this is 2 times the rotational work of 64.0 joules, and divide that by this expression for the rotational inertia. That's 1/2 times the mass, that's 85.0 kilograms, and the radius of 0.320 meters and squared. All right, let us have the calculator aid us in this calculation. So let's first start off with second square root, and then let's do alpha F1 to set up with a numerator over denominator a fraction stack under a square root. So let's perform 2 times 64, ignoring the fact that the calculator does not care about significant digits, over, let's do 0.5, that'll be easiest to calculate with, times 85 times 0.32 squared. Okay, so it looks like we've got about 5.42, let's write this down, 5.42, and that's radians per second, because it's an angular velocity. Let's make sure the units work out. Joules is a kilogram meters squared per second squared. The kilograms divides out here. When you divide out meters squared, you get 1 over seconds squared. The square root of that is just 1 over seconds. But wait, it's 1 over seconds, but that's a counting unit, which is radians, per second, which is our angular velocity. So notice this problem involved energy, involved work, involved rotation, and we used torque to get us to a rotational work. And thus, that rotational force, given a rotational displacement, gave us a rotational force. Okay, so I hope that makes sense. So, thank you very much for watching this video, and thank you for supporting High Peak Education. Please smash that like button if you enjoy this content. Please share this video amongst your social network. Please, I look forward to your comments, and please subscribe to the channel to grow the channel. I will see you in the next video.